Ultra HDI technology is pushing PCB manufacturing into a completely different level of precision. And because of that, many traditional PCB design habits are starting to become risky. In the past, engineers often focused on one question: what is the smallest feature the factory can build? But in today's UD environment, that question is no longer enough. The better question is, what structures can remain stable across real production conditions? Because manufacturability is not defined by a single successful sample. It is defined by repeatability, yield stability, assembly consistency, and long-term reliability. That is where many UD projects begin facing problems. On paper, extremely small geometries may appear achievable. Modern fabrication equipment is incredibly advanced: laser drilling, high-resolution imaging, precision plating, advanced OE, and tight process control. But real manufacturing always contains variation. Materials expanded and contracted. Copper distribution changes plating behavior. Registration shifts during lamination. Thermal stress accumulates through multiple process cycles. And as feature sizes continue shrinking, the available processing margin becomes smaller and smaller. At that point, even minor variations can start affecting yield or reliability. This is why simply designing at the edge of published capability limits is often not the best engineering strategy. In many cases, the more successful approach is designing inside a controlled manufacturing windows instead of chasing the absolute minimum geometry. For example, via architecture has become a major reliability consideration in UD designs. Stacked microvias can increase routing density, but they also introduce higher process complexity and stress concentration. In some applications, staggered via structures may provide better manufacturing robustness and more stable long-term performance. The same principle applies to dielectric thickness, solder mask strategy, copper balancing, and fine pitch assembly design. These are no longer secondary manufacturing details. They are now part of core design engineering. Another important shift is that PCB layout and fabrication engineering can no longer operate independently. As UD structures become more complex, decisions involving stack-up design, via strategy, material selection, and process sequencing increasingly requires early collaboration between design teams and manufacturing teams. Otherwise, a layout that looks efficient in CAD may become extremely difficult to manufacture consistently at production scale. And this is probably the most important point. In advanced PCB technology, success is not determined only by how small the features are. It is determined by whether the design can survive real manufacturing conditions, with stable yield, stable reliability, and stable assembly performance. That mindset is becoming essential for the next generation of UD engineering.